Now, that was quite successful to get the ground state. We might want to try to find another state. So to find the next state, we want to find another function that happens to be its own Fourier transform. Now, not necessarily too many things just spring to our minds out of nowhere, but if we sit and think about it a little bit, there's some things that might really help us with this. We know, for example, I'm going to just make a sketch of what it has to look like. We can make a sketch, and we know the next state, because of our parity symmetry, right, has to be an odd function, so it has to kind of go through 0 like so, and it eventually has to go over into some kind of classically forbidden region on either side. So we know phi naught will have to look something like this. And there's sort of an easy way to, this is phi 1, I'm sorry. This would be the first excited state. There's kind of an easy way to make our function do this, right? I mean, we know, here I'll write phi. This is just a guessing game right now. I could take my original Gaussian, because we know the original Gaussian kind of really works for us very well. And we could, for example, just take a guess and multiply it by x. That would definitely make something that looks like this. Now, the big question as to whether or not this is really a good candidate would be then to consider what would happen if I look at this in the momentum space representation. Now, at first, it might seem a little tricky how to get this. We'd have to do some crazy Fourier transformation. But remember, we have all these beautiful operators we can use for each of the different representations. So this here, remember, I'm starting with my phi naught, and I'm just multiplying by x. But x is really just the position representation of the x operator. So the corresponding function I would have in the momentum space would be the original momentum space wave function, which is e to the minus k squared divided by 2, right? That's the phi tilde naught. And then what I would apply to it would be then the momentum representation of the x operator. And that will then give me the momentum representation of this function. Now, the momentum representation of the x operator would be I times d by dk. And in fact, if I were to take the derivative of this function, I would get, we've just done it, right? In real space, in position space, it's the same in momentum space. I'll get a minus sign, a factor of k, but I had an I, so it'll be minus ik e to the minus k squared over 2. And sure enough, right, these really are exactly, up to a constant that I'm not worried about, exactly they're the same function, right? So these here are another pair of functions that are their own Fourier transform, and we've got one node. So this is a great guess then for the first excited state. So let's, and we could confirm that, and in fact, this is going to work, and we will actually prove that it is in the future lecture. But this actually is a good guess, and it turns out to be correct. So this would be x times e to the minus x squared over 2. And if we want, I'm just going to claim it for now. We can prove it later. But if you stick it into the Schrodinger equation, it will work, and you will get your first excited state energy, which will work out now not to be 1/2, but to be 3/2. Okay, let's try to go further. So this was a good way to try to get at phi 1. Now for phi 2, we could try exactly the same procedure, right? So let's try here. So this was for phi 1, right? So for phi 2, for the next phi, right, what I could do is I could multiply by x yet again. So let's, I'm going to write an x here, right? I can do x multiplying yet again. I want us actually to leave a little space in here because I want to do a little thinking about actually what we're doing in a moment. And then that's going to apply to phi 1 because we know phi 1 actually did work out to be his own Fourier transform. And in the parallel operation, I could be trying to compute phi 2 tilde, would be a similar operation applied to phi 1 tilde. And the operation that corresponded to x, as we had seen, would be doing I d by dk. Now here you can see we're going to run into a little trouble, right? I can actually compute this. I know that phi 2 then is going to be, if I'm going with my above guess, x times phi 1. That's going to give me x squared times my Gaussian, e to the minus x squared over 2. Whereas over here, my phi 2 tilde is going to be, I'm going to have to take I times the first derivative of phi 1. But if I were going with this guess construction, phi tilde 1, remember, was just I d by dk on phi tilde 0. That's how we got it in the first place. And that by the time I apply this operator twice, it'll be minus 2 derivatives of my Gaussian. And we've already computed what 2 derivatives of our Gaussian looks like. We happened to compute it with x's, but it was exactly the same Gaussian. And when we took that second derivative, we got minus 1 plus x squared. So in this case, then, those 2 derivatives are going to give me, well, I have my minus sign, but the second derivative part will be minus 1 plus k squared times e to the minus k squared divided by 2. And at this stage, I hope you can see where we've run ourselves into some trouble, right? This function is not the same as this function. Some extra piece came in here, and it kind of ruined our pattern. And these are not their own Fourier transforms, so we know for sure this is not going to be the second state. So we need to think a little harder to try to repair this. And I think you can see exactly where we had gotten into trouble. The issue is that we are not applying, actually, the same operation in position as we are in momentum. We broke the symmetry between position and momentum, and so eventually, as I keep applying different operations in the different spaces, it shouldn't be a giant shock that I end up with results that start turning out to be different. So we want to find an operation that works, something like this multiplying by x, but which does the same thing in both of the spaces. In one space, I'm multiplying. In the other space, I'm taking a derivative. So if I want to restore the symmetry, it's natural to ask, well, what would happen if I were to add in, say, some amount? I'm leaving a blank space here so we can engineer things a little bit. Some amount of an x derivative, and then do the corresponding thing in the other space and see if the two operations correspond or not. So here's the logic of how that is going to work, right? X we used before, well, this was just the x operator in the position space, and that works out very nicely because here we are applying the x operator in the momentum space. Likewise, the partial x derivative is very closely related to the momentum operator, right? Remember, momentum operator in position is h bar on I times the x derivative. So therefore, the x derivative itself must be I divided by h bar times the momentum operator. So the corresponding piece over here would be I over h bar times the momentum operator now in the momentum space. And we know what that operator is. That's just h bar times k in the momentum space. And so when I multiply these, that turns out to be just I times k. So the corresponding operation in the momentum space would be ik. And if you look at these, it's perfect, right? They came with exactly the same prefactor, right? Except for, okay, there's an overall constant, a factor of I that I could pull out, but otherwise these would be identical if, for example, I put in a plus sign, like so, because then this is just an extra factor of I that I don't care about, and then k plus d by dk acting on my preceding wave function, and I now have an operator that is guaranteed up to a factor of I to give me exactly the same function back again over and over again, and I now can generate an entire sequence of functions that are their own Fourier transforms. Now this operator is so important, we like to give it a name. I'm going to call this operator the A hat operator. There's nothing special about the name A hat. It's just the first letter in the alphabet, but that is the standard definition of a very important operator that occurs over and over again in the theory of the harmonic oscillator, in the theory of photons, in the theory of phonons in solid-state physics. It's a very critical operator. Great, so now we've got a way of generating our function phi 2. Let's try it out and see how we do. What will our new state be? So let's try. And we will apply A hat on our ground state, phi naught, which will equal now, in the simplest representation, right, x plus d by dx, very simple, applied to my Gaussian, e to the minus x squared on 2. And as we apply this, we will stay organized and keep factoring out that common factor of the Gaussian. The first term, of course, just gives me x times my Gaussian, so I can put an x in my parentheses times my Gaussian. My next term, I take the derivative. That will give me the Gaussian back again, which I already factored out, times the derivative of the insides, which would be minus 2x over 2, or, minus x. That's not good, right? That just gave me 0. Now, it's true, 0 is its own Fourier transform, so I would have the same function in both spaces, but this actually is not a bound state. It just represents a state with 0 probability. So this choice of operator, while guaranteeing the self-Fourier transform property, unfortunately just gave us back 0 again. So we can't really use this to construct new excited states. But we've just learned a very important identity and fact about our operators, so I'm going to put a box on this. This one is very critical. All right, well, this here didn't go so well. Maybe we can adjust things, right? It's not really nice that when we added these, we ended up getting 0. Both terms did give us x times our Gaussian, right? So it did get, both terms tried to give us the first excited state. They just ended up canceling. So we could consider, in fact, a different operator. We could consider, say, subtracting in here. If I subtracted, then I'm definitely not going to get 0. But if I do that, I'm defining a new operator. So the plus goes with the A hat. The minus then, so I'll put a little slash here, gives me another operator. Its formal designation is A hat with a superscript dagger, it's called. You can think of it as a little plus sign because it will succeed in getting us higher and higher energy states. If we think about what the action of this proposed operator would be in the momentum space, of course, that would just make this a subtraction instead. And if I continue to follow my logic, next thing that I did is I factored out the I, right? And when I factor out that I, now I would be left with a minus k. So I actually want to factor out a minus I. So let me say in the first case I had factored out the plus I. Now I'm factoring out a minus I. And when I factor out that minus I, I'm left with k. And then on this side, when I pull out a minus I, I'm left with an extra minus sign on the inside. It should be minus d by dk. So I would include a lower minus sign. But notice, right, it's the same operation. Now I've got this factor of minus I pulled out. That's just a constant I don't care about. What's left on the inside is k minus d by dk, which corresponds precisely to my x minus d by dx. So this A hat dagger also preserves the self-Fourier transform operation, and that then gives us a way, perhaps, of generating more excited states. So Let's write that out a little bit formally here as I'm putting boxes around my key things. So A hat was defined this way. A hat dagger, which I'm now much more hopeful about, is defined as the subtraction version of these two. And let's try now with the A hat dagger. So if we apply that to my ground state, we already know this will work. So that will be x minus d by dx of an e to the minus x squared on 2. Being organized as we like to be, we will factor out our Gaussian. The first term gives me just x, as we had discussed. Now I have minus the derivative. The derivative gives me the Gaussian. It pulls down a minus x, but there's a minus sign here, so it's x plus x. And I get 2x times e to the minus x squared over 2. And once again, I'm not worried about constants right now today, so I know this actually is indeed giving me, we've already checked it out, this does give me the first excited state, and, or at least I had claimed we could show that that is an eigenstate. We still have to prove that, but it does. And in fact, it also then gives us a state with the energy that I had shown you previously. So that works. So I can get the first state from the ground state. The big question now is, well, what happens if I try this again on phi 1? As we've just described, what I generate will automatically be its own Fourier transform. So I don't have to check on that anymore. I just have to make sure I don't get something silly, for instance, like a 0. So if I apply this operator, this will be x minus d by dx. Phi 1, which we've just computed, was 2x times e to the minus x squared over 2. And again, I'm not terribly worried about my constants, but we will, try to preserve them. So I'll factor out my 2. That's pretty easy. I then will gather all my terms together and pull out at the end of the day the e to the minus x squared over 2. So let's see what we get, right? The 2's been taken care of. So first I have x times my Gaussian. That gives me x squared times my Gaussian. Here's my Gaussian, so I can just write my x squared. Next, I have to take the derivative of x times my Gaussian with a minus sign. Well, when the derivative hits the x in the product rule, that will just give me a minus 1 from this minus sign. So there will be a minus 1 times my Gaussian. Finally, the derivative in the product rule will hit the Gaussian. When it does, it'll give me my Gaussian back again. An extra factor of minus x will come down. So I'll have minus x coming down, multiplying this minus x for a plus x squared, like so. And if I like, I could rearrange this a little bit. So this will be twice of 2x squared minus 1. Multiplying my Gaussian. So I'd like this firstly because you will notice it's not 0 everywhere. That's very good. So it's a good candidate state. If I were to sketch this candidate, so I could call it phi 2 question mark. We haven't really proved it yet. We know that very far away, I get positive numbers. This will be positive far away times a Gaussian, so it's going to be decaying to 0. Something like so, far away. When x equals 0, this term gives me actually minus 2. So it'll be down here at minus 2. And it has to be a continuous function. And it also kind of has to look like a Gaussian. So it's kind of like a Gaussian at the origin, right? But it has to cross the axis to come down like so. My function will look something like this. And I want you to notice it's got exactly 2 nodes. So it's a very good candidate for the second excited state. And eventually we will be able to prove in the next lecture that it is indeed an eigenstate of the Hamiltonian. And we will be able to compute its energy. And it will turn out, this is just a claim right now, that this energy is going to become then 5 halves. And we'll come back later to the meaning of that particular energy sequence. And then finally, notice I can just keep this procedure up. I can take this operator, I can apply it to my nth state, and it will actually give me my next state. And if you just think about this type of an operation, notice that then phi n is the my operator applied then on the preceding state, and you could write it then as the operator, and the preceding state is the operator applying to the state before it, and you can continue in this way, and you will realize that at the end of the day, to get the nth state, I will get there by applying this dagger operator n times onto the ground state to get me my nth excited state. So we have a procedure for getting all of these states. Right now, we're not sure that they give us the eigenstates. That's something we definitely have left to prove to ourselves. So I'll put little question marks on the things that we need to prove. But we've got a very good framework now in place. These things here we definitely had proved, which were very nice. The only other guess we had here was that, well, is this really phi 1, and is this energy? And we will take up all of these topics then in the next lecture.